three-phase motor stator connections. In this presentation, we're going to be looking at how the windings of the stator in a three-phase machine get connected out to the supply conductors. We're also going to be focusing our efforts on the motor lead labeling and also the motor lead connections themselves, because there's different combinations that we will see. Now, the types of different stator connections that we have in the electrical industry are labeled as per the number of leads that come out of the motor junction box. We have 3 lead motors, 6 lead motors, 9 lead, and 12 lead. These being the most common forms of three-phase machines in North America. What we're going to start with is 3 lead machines. Now, 3 lead machines can be manufactured by the company who builds them as either Y or delta, the windings inside the stator. The way that we label these leads is by associating them with a T. So T1, T2, T3. The way that we then assign these is to start at the top and work our way around in a clockwise fashion. T1, T2, T3. In the same way that on this one, we would have T1, T2, and T3. Now, what's important to keep in mind is that the T1, 2, and 3 are the terminals or the leads of the motor that the three-phase supply will connect to on every one of these motors that we're going to be looking at. Regardless of how many leads, these are the ones that will have the three-phase. So I'm going to do my three-phase supply connections in brown. In the same way, we would see this. Are red, black, and blue connecting to T1, T2, T3. And so for a Y-wound 3-lead motor versus a delta-wound 3-lead motor, the installer would see absolutely no difference in its actual wiring. So this is the most basic type of 3-phase motor. Let's take a look at a different one. This one is for specialty applications, and it's called a 6-lead motor. Now, a 6-lead motor is unique specifically for this application because it's meant for specialty starting. We can use this type of motor to reduce the inrush current when the motor starts, but we will cover that in a later presentation. What's unique about this motor is that there are 6 wires that will terminate to it from the motor starter, which would be over here. The labeling of these leads will be in much the same way. I've drawn them horizontally in this particular motor because it can be connected in either Y or delta. And you can see here that it will be started with the windings in a Y connection and run with the windings in a delta connection. Now, how all of that takes place is again due to the starter, and we will cover that in a later presentation. So first off, let's just label the windings. T1, T2, T3, T4, T5, and T6. Now this one, we need to make some additional connections on, and I'll just show you how we're going to do that. This would be in a Y formation at start, which means that T4, T5, and T6 will all be connected together at the starter. The 3 T terminals 1, 2, and 3 will be connected to the 3-phase supply. Now, this particular motor can also be run in delta. So it's started in Y and then it runs in delta. Well, delta is a little bit different. Now we're going to label each of these windings, T1, T2, T3, T4, T5, and T6. But now I'm going to put them in delta. And in delta, it's a little bit different. We have this. And then this one connects all the way back to the beginning. So bizarre, it's as if they're all in series, which they kind of are. Now, where do the 3-phase supply connections go to? Well, they go to T1, T2, and T3. Now, the Y delta motor or 6-lead motor is probably one of the more quirky ones that we get to work with, and we will cover them in much greater detail when we start getting into reduced voltage starters. For now, we simply need to know how the connection would take place and which T terminals would be connected together. Let's take a look at the next type of motor. This is the most common type of three-phase motor that we encounter in the field. It's 9 leads and it's dual voltage, and that means it can run on 2 different voltages. Now, it will be manufactured in either a Y wound formation or a delta wound formation. So it's one or the other, and the manufacturer should state this on the front nameplate. Let's take a look first at a 9-lead dual voltage Y motor. Now, this is going to start one of our very standard diagrams and also how we are going to label the T terminals. So we've got 1, 2, 3, 4, 5, 6. We have 2, 4, 6 windings. Each one of the circles indicates a lead or wire that comes out of the motor junction box, and there are 9. This is not a lead, it is a star point that's made by the manufacturer, and we don't have access to it. So let's start with the labeling, because the labeling is one of the more important aspects. We're going to start at the very top, and the very first one is T1. We then label the external or the furthest terminals away in numeric order. T1, 2, 3. Now we go back to the top and we start on this terminal, T4, and we continue increasing or ascending in our numeric number, T5, T6. Then we start again at the top, T7, T8, and T9. So what you have to do is start at the top, work your way from outside, so outside terminals to middle. And move in a clockwise direction. If you follow these 3 steps, you should be fine in a outward or a descending spiral going all the way down through all the numbers. All right, well, let's take a look at this motor and the 2 different voltage connections that we can have. Now, we already know from nameplates that many motors have diagrams that tell us how to connect. So here is a 9-lead dual voltage motor. It's a Y wound, and its rating on the nameplate is 234/60. The very first thing I'm going to do is I'm going to label all of the leads. So T1, T2, T3, T4, T5, T6, T7, T8, and T9. So now I've got all 9 of my leads identified. Now this is going to be connected for a high voltage connection, and we can see at the top it says 234/60, so this means it would be the connection for the 460 voltage. Now, in order for me to do this, I have a choice always. I can connect the windings that I see in front of me in series or parallel. When we have a high voltage connection, the standard is always to connect the windings in series. And so what this means is that we're going to be connecting all of these windings so that they make one large Y connection. So what we've done is connected 4 and 7, 8 and 5, 6 and 9. They're tied together, and then we take our 3-phase supply and we connect to T1, T2, and T3, like in all of the previous motors. On the actual motor itself, with the wires coming out, it's going to look very similar. We're going to have 3 leads that simply come and connect with morettes to our supply conductors. And then we're going to have 2 wires connected together under morettes. We're going to have 3 of those pairs. So we'll have 1, 2 wires under a moret. 1, 2 wires under a moret. And 1, 2 wires under a moret. So you're going to have 6 morets in there. And these 3 pairs won't connect to any supply conductor. So for the 9-lead dual voltage Y, it is the high voltage connection that we've looked at here. The connection is series, and the series connection requires 478596 to be terminated together, and then the supply conductors coming in on T123. Well, let's take a look at the same motor, but now we're going to look at it in low voltage connection. So it's exactly the same motor, exactly the same, but now we're going to connect it for the 230 volt range. So this is considered a parallel connection. In the previous connection, these being in series meant that the full source voltage, or the phase value of that source voltage, would be divided equally across both windings. In the parallel connection, we're going to have the full phase voltage across each winding. So let's take a look at how this is going to lay out. First, assign labels to each of our terminals. T5, T6, T7, T8, and T9. Once we've got that done, now we can start looking at the parallel connection. Now, often this type of connection can be displayed at times a little bit different, and they'll show something like this. And they'll show 2 Y-connected windings and this, along with the source voltage coming off. So this is an alternative means of showing that we have 2 Y formations connected in parallel. So how do we accomplish that? Well, the way that we do it is we tie T1 to T7. We connect T2 to T8. And finally, T3 to T9. Once we've done that, we now need to provide another star point for 4, 5, and 6. And so we have to connect all 3 of them together. So there's one and the next one right here. Finally, our 3-phase source conductors connect to T1, T2, and T3. Again, what this would look like in the motor junction box is very similar. We're going to have not only one wire connecting, so the phase conductor to T3, or the line conductor, but also T9. So there are 3 wires that would be connected together under a single moret. 1, 2, 3. And then we'd have the same thing for the next line, or the next line. So 1, 2, 3. And finally, 1, 2, 3. Now, what else do we have? T6, T5, T4 all need to be terminated together. So all 3 of these would be connected together under a moret. So we would have 1, 2, 3, 4 morets. One of these groupings would be 3 conductors, and they would not connect to a line conductor. The other ones would be groups of 3 conductors under one moret. In this way, low voltage connection, we have the full 230 volts being applied across each individual winding, or I should say the phase value of 230, because this being a Y connection would be the phase voltage for a line value of 230 volts. Well, let's take a look at the next type of 3-phase motor, and that was the other 9-lead. So the other 9-lead is the delta. Now the delta connection is going to be connected in much the same way. We'll have a series and a parallel connection. But first, let's focus on the T terminals. We need to assign them in the exact same way that we did in all of the previous motors, which is starting at the top, working our way in a clockwise spiral through the system. So T2, T3. We then go back to the top and choose the next terminal down. So we're going in a clockwise circle. Numeric ascending order, T4. Go around, T5. Go around, T6. All the way around again, T7. Around T8 and around T9. The labeling is important. If we don't have the diagram in front of us from the manufacturer, we need to know how to assign this so that we can figure out the connection. All right, well, let's take a look then at a 9-lead dual voltage delta wound motor, and we're going to look at it for the high voltage connection first. So here is our 9-lead dual voltage. Let's first start by labeling all of the terminals. T1, T2, T3, T4, T5, T6, T7, T8, and T9. Now that they're all labeled, we can look at making the connection. Now remember, in the last one, we said a high voltage connection requires a series connected winding array. This is the same thing that will happen on the delta. We're going to connect the windings in series, and the series connection is always the easiest. So we would be connecting this for the 480 volt range that's given on the nameplate. In order to connect them in series, we're simply connecting each of the windings together, 4 and 7, 5 and 8, 6 and 9. The main supply 3-phase connections then come out of T1, T2, and T3. In much the same way, we see the connections down at the motor of having an individual wire coming out to T2, T3, and T1, and then 6 and 9 tied together. So that would be 2 wires like this. Another 2 would be 4 and 7. And finally, the last 2 would be 5 and 8. So in total, we'd have 6 lead connections with Marats, or 6 Marats. Notice that this is identical to one of the Y connections in the types of connection, like how many wires under each Marat and the lead number for each wire. All right, well, let's take a look at now the low voltage. The low voltage connection for Delta may be the more tricky one that we accomplish while in apprenticeship training. This one will, again, because it's low voltage, require a parallel connection. In much the same way that we could have 2 separate delta ranged windings that had us connecting them in parallel, and then the power conductors connecting to one side. So we're going to connect these in parallel. First thing we need to do in order to make this 240 volt connection work is to get the terminal numbers assigned. T1, T2, T3, T4, T5, and T6, T7, T8, T9. It's getting repetitive. So now let's look at the connection. So in order for us to make a parallel connection, we need to assign or connect the power conductors from the line A, B, and C to more than just T1, 2, and 3. So we're going to do this. T1 connects to the main line conductor. It will also get moretted to T6 and 7. T2 is also going to have a line conductor, and it will terminate also to T8 and 4. And finally, T3, which connects to a line conductor, will terminate also to T9 and T5. Gets a little bit confusing, but if you keep things consistent and neat, you should be off to the races. Our line conductors go to T1, 2, and 3, and we have our completed connection. Now, which wires would then be connected down here at our motor? Well, T3, T5, T9, so that's 3 motor leads plus the line conductor. So we would have 1, 2, 3 motor lead conductors connecting to one of our line conductors. We would then have the same thing again, 1, 2, and 3 connecting to our second line conductor. And finally, the third one here, 1, 2, and 3. So we'd have 3 morettes, and those morettes would contain all 9 of those conductors as well as the 3 line conductors that are going in. So again, what's happening in this system? Well, each one of the individual windings in this motor, because we're in delta, is receiving the full 240 volts that is being applied from that 3-phase line connection. Well, let's now transition and take a look at a somewhat unique type of motor. It's not as common any longer, but it is still out in industry. This is called a 12-lead dual voltage, although you'll find it can actually be used on more than just on 2 voltages. Now, this motor can be connected by the installer as Y high voltage, Y low voltage, delta high voltage, or delta low voltage. So there are 4 different connections. Now, why would they produce such a beast? It's simply to allow for more flexibility. If they can sell one motor to 4 different individuals in 4 different countries for 4 different voltages, it brings the manufacturing costs down and reduces the stock that wholesalers need to have on hand. So the connection is chosen based on the 3-phase source that happens to be available. Well, let's take a look at how this is going to then take place. Now, I've chosen to sketch my 12-lead motor for the Y connections in a Y arrangement. But keep in mind, a 12-lead motor, since it can be connected in Y or delta, really to make it consistent for every single sketch, you should place them all horizontally, which makes it so much harder. So we typically do not do that. All right, so very first thing, let's start with the labeling. Now, the labeling of each of these T terminals is going to be pretty much the same as all the others we've done. Now, remember on the Y system, we started at the top and we went around in a clockwise direction and we ascended or increased the number of the T terminal as we continued along. So T4, 5, 6, T7, T8, T9, guess what? We start again here, T10, T11, and T12. Now at this point, you can probably see that the only thing that differentiates a 12-lead motor from a 9-lead is that there is no star connection. So we have to make that star connection ourselves. Now we're going to do a high voltage connection for Y. And high voltage in Y means that we are going to make a star connection in the center and then connect all the windings in series. So I'm just going to put a note here and say, yes, we continue to connect in series. Now notice I've placed here each winding for this particular motor. I've chosen to give it the rating 240 volts. So when we connect the source supply, we should be able to determine here what voltage is being used for this particular connection. So what voltage would have to be between these 2 lines with this particular rating and this connection? Well, in this connection, it means that I would have required 240 volts to be dropped across each of my windings. That would mean that the total phase voltage that is required would be 480 volts. And therefore, if the phase value is 480, the line value must be root 3 larger. So that would be 480 times root 3. And if I get my calculator out, 480 times root 3 gives me 831.3 volts. That would be the required line voltage for this particular three-phase 12 lead connection, which is Y, high voltage. So what would the connections look down at the motor? Well, there's quite a few connections now, isn't there? We're going to have one wire terminating to each of the line conductors. So 1, 2, 3. We're then going to have 2, 2, and 2. So I have 3 groups of 2 wires. 1, 2, 3. And then I also have this group of 3 in the middle. So 1, 2, 3. And this is what the final connection would look like. Those connection boxes have to be sized large enough in order to fit all those conductors as well as the morettes. But of course, we don't determine that. That's made by the manufacturer. All right, well, let's take a look now at a 12 lead Y in low voltage. Same motor again, but this time we're doing a low voltage connection, and the low voltage connection is going to, again, just like before, low voltage is parallel. All right, so first step, we're going to label all of the leads. T1, T2, T3, T4, T5, T6, T7, T8, T9, T11, or 10 rather, T11, T12. All right. Now, if we want to place this in parallel, a lot of similarities between this and the 9-lead Y. We are going to have a Y connection in the middle, or star connection. We're also going to need to have a connection from T1 to T7, a connection from T2 to T8, and a connection from T3 to T9. In addition to that, we need to have 4, 5, and 6 tied together. Now, finally, our line conductors connect to T1, 2, and 3. So in this particular scenario, we've done a parallel connection. And if we wanted to determine what voltage would be present, or what line voltage of three-phase source would we need, well, we need to utilize our abilities of understanding with voltage and parallel connections. Each of these is rated for 240 volts. Since they're in parallel, they do not add. It's as if we have 2 Y connections. So that would mean the phase voltage is 240 volts. And if we wanted to know the line voltage of this particular three-phase source, we would take 240 volts times root 3. So 240 times the square root of 3 gives me 416 volts, or 415.6. And that would be the line voltage of three-phase source. So what happens for the connections down at the motor? Well, we have 1, 2, 3 wires that all connect together under a moret. This is my line, T3 and T9. So there's 2 motor leads that connect to each of my individual line conductors. So 1, 2, 3, and 1, 2, 3. In addition to that, we're going to have 10, 11, 12. And we're going to have 6, 5, and 4. So in total, we'd have 5 morets. Now, this is only 2 of the different connections that we could possibly have. So let's take a look at the next one. This is my 12-lead motor that is now going to be connected in delta for high voltage. Well, just like before, we're going to start with labeling of all of our individual terminals. Now, this one's a little bit more tricky, perhaps, because we need to now decide which one do we start on for T1. We always start on the right-hand side. So this right here is T1. We go all the way around. This one is T2. All the way around. This one is T3. And now it's just going through the circles. T4, T5, T6, start again here, T7, T8, T9, start again here, T10, T11, T12. All right, so we're doing a high voltage delta connected 12 lead. And again, just like the 12 lead Y being very similar in its connection to a 9 lead Y, the 12 lead delta is going to be very similar to a 9 lead delta. And what that means is that we are first going to connect the tips or the outer reaches of our delta together to make a triangle. We're then going to make it a series connection by doing the same connections as before. 4 and 7, 5 and 8, 6 and 9 all tie together, and our line conductors continue to connect to T2, T1, and T3. Now for this particular motor, what voltage of three-phase line source would be used? Well, each winding is rated 240, and we have placed it in series. And if we look at the voltage values given here, each winding continues to be rated for 240 volts. And since they're connected in series, in delta, the phase voltage would be equivalent to the line voltage, meaning there would be a 480 volt line value for the three-phase. So 480 volt would be utilized for this connection. Let's take a look at the terminals down at the actual motor box. It looks like we have 1, 2, and 3 wires connected together for each one of these line connections. So 1, 2, 3, 1, 2, 3, and 1, 2, 3. So that's T2, T10, and the line conductor. T1, T12, and the line conductor. T11, 3, and the line conductor. 6 and 9, 4 and 7, 5 and 8. That is 3 pairs of wires. 1, 2, and 3. So a 12 lead motor, once you get the hang of it, not that much more complicated. All right, and finally, the last motor we're going to look at is the 12 lead, but this time it is delta and low voltage connected. Now remember, in parallel, we are doing, with low voltage, we are doing a parallel connection. And so we're going to look back if we are unsure how this connection should take place at the 9 lead low voltage delta connection. Before we do anything, we'd better label every single one of these terminals, starting on the right-hand terminal, T1, and going around in a clockwise direction. T2, T3, T4, T5, T6, T7, T8, T9, T10, oh, almost missed that one, T11, and T12. All right, let's do a parallel connection. Now, a lot of similarities still. We're going to create those corner points to our triangle, and then we're going to connect these down to 4 and 8. So I'm just going to go from T2 to T4 and T8, T3 to T5 and to T9, T1 to T6 and to T7. Line conductors continue to terminate, like in every other three-phase machine that we've looked at, to T1, 2, and 3. So with this connection, We have quite a few conductors under one moret, and this is why in the larger conductor or larger motors, you'll typically see that there is an eyelet that is crimped onto the end of the actual wire, and that way you can bolt multiple conductors together with a small 832 or quarter-inch bolt, and then wrap the whole thing in electrical tape and rubber tape and all the rest. So T3, T11, T5, T9 are all connected together. That's 1, 2, 3, 4, 5 conductors. So 1, 2, 3, 4. Plus the line conductor is 5. 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. So in this connection, all we have is 3 morets, and because we have the everything connected together, it is in parallel, and the voltage of this particular system, if we were to look at the line voltage that could be used here, well, we know that each winding is 240 volts. And we also know that in parallel, the voltages do not add, it is simply the full line value. And because of that, we would have a 3-phase line value voltage of 240 volts. So there you have it. One motor could be connected to 3 or 4 different 3-phase voltages depending on where in the world it happens to be used. These are the most common 3-phase stator connections that we are going to see, and they are the same types of connections for different types of alternators, synchronous motors, wound rotor motors, and SCIM motors.